Okay, so again, the universal shunt meter. This is a meter that makes it possible to always have some sort of resistance in line with the current that you're measuring. It's a way to protect your circuit, keep your meter from getting damaged, keep from blowing fuses, things like that. This is a better version than, like I said, of the shunt meter that we did when we were talking about just parallel circuits. How we're going to do this is we're going to go range by range, look at what's going on, and we're going to solve for any of the variables that we can. The goal is, as this progresses, as we go through each range, we want to solve for at least one of these values. We're going to solve for our R1, R2, and R3 to give us the three ranges that we want. So range 1 is 5 milliamps. Range 2, we want to be able to measure a max of 17 milliamps. And range 3, we want to use 125 milliamps. Again, this is just more applications of series parallel networks. This is also going to help you guys practice with your redraw skills and figuring out what's now in series, what's now in parallel, how everything is connected together. So, given the information, what we need to do is we need to redraw this so it makes it a little bit easier to see what's going on, eliminates the different switch positions. We want to just make it as simplistic as possible. So what we're going to do is we're going to treat each of these guys as one of these points. We'll call this A and B just for when we're labeling this thing. So the first thing we have is we want to look at what is connected at point A. And so this is for range 1. So point A is connected to what? R1 and the meter. R1 is connected to R2. R2 is connected to, okay? And then R3 is connected to the meter and point B. So range 1, here is our redraw for this circuit. When we redo these, we want to get them so they're similar to this. Everything lines up and it's easier to see what's going on. Okay, so the first thing we have to figure out is what can we solve for in this circuit with what we have right now. We can solve for the voltage of the meter. So we have 600 microamps, 1.2 kiloohms, and the voltage of the meter is going to be current times resistance. We get 720 millivolts. Okay. What else can we do? What are they using our rules? What can we infer? Maybe not necessarily the specific values, but how do we get some of these values?
Well, the other side, like R2, R1, R2, R3, we know that that's going to also have 720 millivolts.
Okay, we know that this side is going to have 720 millivolts as well. Okay, what else? What about currents? Right now we're just going to start labeling these things, not necessarily solving for the exact values. Okay?
It's going to be the original numbers, 15 minus the meters.
Okay. So what current do we have here? 600. This is also our I meter. We have our range current. So in this case, we've got 5 milliamps. Between what? Yes. Okay. So the other thing we have is we have another current going through here. Let's label this guy as I shunt current 1. Okay, IS1. Because this is the first current that we have going through shunt resistors. Does everybody feel comfortable with what we've got so far? We haven't talked about anything new. We're just applying all the different rules. So let's write out a couple equations. I shunt 1 is equal to what? I range 1 minus I meter. Okay? What else do we know? Where in this circuit, how are we going to find resistance? Do we have a place that's going to give us max or min resistance? Yes, okay. So that's going to give us a minimum amount of resistance. So what is R1 giving us? Where we're at right now with range 1? Max resistance. Because everything we have is in series with each other. There's no other way to get any more resistance out of this circuit. So our R shunt total, so all total resistance we can get in this guy, is equal to R1 plus R2 plus R3. Anybody have any questions or concerns where we've come up with this stuff?
So R1 and 2 and 3 are all in series?
At this stage, yes, they are all in series. That's going to change when we start going to the different ranges. But nowhere else are we going to have any more resistance than what we have right here. Yes. Yep, because these guys are all in series, this I shunt 1 current is going through every single one of those guys. What else can we find? So now that we have a couple of formulas, we have some values, what can we solve for? Exactly. So let's solve for that. So I shunt 1 is equal to I range 1 minus I meter. So I shunt 1 is equal to 5 milliamps minus 600 microamps. 4.4 milliamps. The end goal of this, like I said, is we're trying to design this meter to give us these ranges using this meter that we have.
Do we use the voltage from the meter to solve the resistances then over?
Yes, then we can. At this point, now we're just using Ohm's law. We have a current, we have a voltage, we can solve for the resistance through this point. Okay, so now we have the resistance for our shunt total is equal to I shunt 1 times, the voltage of the meter divided by the I shunt 1. So this gives us 720 millivolts divided by 4.4 milliamps gives us how much ohms of resistance? Okay. Okay, so we're able to find our total resistance of this circuit. Is there anything else that we could solve for at this point? We will. Can we determine that right now, though? No. We don't have enough information. We could use Thevenin.
Or couldn't we just solve for like R2, move to R2, and then use those to figure out what R1 would be?
That's where we're heading. Okay? I'm just saying that, do you guys see any other ways that we could solve for any other values in this circuit? That, that's what we will do as well. Okay? We wouldn't get a very good voltage. So in this case, Thevenin's not going to work because we don't have very many current paths. We don't have, when we pull that guy out, now those other two resistors are going to essentially disappear, and we're still going to get that 720 volts. So Thevenin's not going to work in this case. Okay? Oh, you'll be begging me to bring back Thevenin here shortly. So this gives us those values. I'm going to write some of these down. So we have our I shunt 1 is equal to 4.4 milliamps. The resistance of our shunt total is 163.636 ohms. Let's see, anything else we have? We also have our R shunt total is equal to R1 plus R2 plus R3. And I shunt 1 is equal to I range 1 minus I meter. We've created these formulas. These formulas are not going to change that much. We're just going to start changing placements of these guys. But for these base formulas, this is what we have to work with. Okay? Any questions about anything we've uncovered so far? We good there? Okay. So now, we're going to flip the switch, and we're going to look at range 2, because there's nothing else we can do at this point with range 1. We're tied. We still have these other options that gives us. So we're going to switch over to range 2. I'm going to do this one in green so we can see the distinction of it. Okay, I'm going to put that up there so we can scroll past it, but we still have a reference to what we're building. I guess I should put R1, R2, R3, and I meter is equal to 600 microamps. R meter is 1.2 kilo ohms, and V meter is equal to 720 millivolts. This way we can scroll past and we still have our base information. So first thing we're going to look at is now we're switching our switch to our range 2. What do we have connected to point A? We have R1 and R2 in parallel. What is R1 connected to? Connected into the meter. What is R2 connected to? R3. What's R3 connected to? Meter and to B. Now that we have this, now we're going to continue on and solve for everything else that we have. Okay? So again, let's look. We have I meter, we have V meter, we have R meter. We have those values. What other values do we have? We have 17 milliamps. And so we have 17 milliamps coming into the circuit. How is this going to break up? Okay.
Is 5 million still going to go to R1?
Only when we were in that position. So we have 600 microamps. Now that's going through R1 and the meter. Yep. So here we have, we're going to label this current as I shunt 2. So how do we solve for I shunt 2? What's our formula? I shunt 2 is equal to range 2 minus I meter. Because again, just like before, we don't want any more current than this guy is rated for to go through it. So we're designing this circuit and the system to allow all the excess current to go through our shunt resistors. So we end up with I shunt 2 is equal to 17 milliamps minus 600 micro. I shunt 2 is equal to 16.4 milliamps. Everybody good there? Okay. Now one of the things we want to look at is we want to solve for these values. Okay? When we're looking at these parallel circuits, we can label these as branch 1, branch 2, just as labels, so we know which side of the circuit we're looking on. So with this, what's one of the rules about parallel circuits? Voltage is what? The same. So the voltage from branch 1 equals the voltage of branch 2, right? So now, what we need to do is let's start putting in some of the values that we can find for. How are we going to solve for the voltage of B1, of branch 1 on this side, the left? Okay? Kirchhoff's current law, which we do have the current. Kirchhoff's voltage law in this case. Okay? Because you have the voltage of R2 and the voltage of R3, right? So the voltage of R2 plus the voltage of R3 has to be equal to the voltage of R1 plus the voltage of the meter. Right? Now, like I said, we're taking our big formula. Now we're going to start expanding this. How do we get these 4 values? Because right now we have 4 unknowns. Well, 3 unknowns because we know voltage of the meter. How do we find voltage for R2? Huh? Yeah, we're solving for them. But what's the formula to solve for voltage? Current times resistance. What current is going through R2? 16.4 also. Let's use our labels for just a second before we get too ahead. Okay? So we take our I shunt 2 times R2 plus what current's going through R3? The same. I shunt 2 times R3 is equal to what's the current on R1? 600 milli, which is I meter. So I meter times R1 plus I meter times R meter. We're just separated out, so we're doing the same thing to everything. We know this value. We know what this is going to come out to be. So it's going to come back there. Now, is there any other way we can simplify this down? How about factoring any of this stuff out? Okay. So we get I shunt 2 is equal to R2 plus R3 is equal to, in this case, we're going to leave, we're just going to combine that together because we know what that value is going to be. Actually, we want to keep that out for a second. So we're gonna keep this side the same. I meter, R meter, just for right now. Okay, looking back, like I said, this is where it's going to take a lot of brain power. Looking back at everything that we have, how can we get this isolated down? Because right now we have our 3 unknowns. We now have them isolated. We need to be able to solve for one of these unknowns. Do we have anything that we can use to maybe swap positions to give us and simplify this down to where we have one single unknown? Resistance total, okay. Doing what? Okay. Right, it will, but those resistor values are still going to stay the same, right? So you're on the right track. What can we swap in and out to give us values to where we're solving for one unknown now? And Zach is on the right track using the total resistance. Not quite. Okay, let's look at this formula. Is there anything we can do to this formula to put in equivalent values to get us down to a single unknown and a known value? Using our shunt total is equal to plus R, or as R1 plus R2 plus R3. Okay, we want to try and get R1 on both sides.
I thought I'm trying to make it so what we have going on in R2 plus R3 is the same as our shunt total.
Okay.
Would you divide I meter by I shunt 2 and then multiply both? Well, divide it by R1?
Yep, here in just a second we will. But we're still left with these two, there are these 3 unknowns. We want to get it simplified down so we have one unknown on both sides of our equals. Is there anything that we can do to swap things in and out to make that happen? We use this equation right here. We have our shunt total is equal to R1 plus R2 plus R3. Does that light it up a little bit? That's still the same formula, correct? If these are equal and equivalent, can we substitute this value in for here?
Oh, yeah.
So let's do that. So we have I shunt 2 multiplied by RST minus R1 is equal to I meter times R1 plus I meter R meter. So all we're doing is we're just taking our formulas that we're given and rearranging them to find new ways to substitute. Because as long as these things are equal, We can swap those in and out left and right as much as we want. Okay? So now when we do that, we have successfully gotten rid of R2 and R3 and put in, we know RST, we don't know R1. We're able to swap out two unknowns for one known and one variable. That's kind of the whole idea of this one. We're going to be using substitution to solve these guys. So now we're going to go through and we're going to carry this all through, because we want to get our R1s by themselves. At this point, we can just use algebra and solve this guy. So we have I shunt 2 times RST, or RTS, either way, minus I shunt 2 times R1 is equal to I meter times R1 plus I meter R meter. Now we're just, like I said, we're just going to use algebra, get all the R1s on one side, and we want to make them, or we want to get it to where those guys are positive. So, IS2,
Yeah, but the next equation, like, goes to the side.
over here.
Yeah, that guy.
So we distributed the I shunt 2 through both of these guys.
Okay.
Because remember, order of operations, we would have to do these parentheses first. We want to get that out of get those parentheses out of there so we can manipulate it farther. We're trying to get all of our R1s together on one side. So now we're going to move this guy. So we're going to move I shunt 2, R1. We're going to remove it from this side. We're going to add the I shunt 2, R1 to the right side of the equation. We're going to subtract I meter, R meter from both sides. So these guys will fall off. Now, what we're left with is I shunt 2 times our resistance total minus voltage of the meter. I'm just going to go ahead and combine that together. Is equal to I meter times R1 plus I shunt 2 times R1. Now we have R1s on the same side of the equation. Yep, now we're going to factor those out. So we have I shunt 2 times the resistance total of our shunt minus voltage of the meter is equal to R1 times I meter plus I shunt 2. What is that value of the last one? The I meter plus I shunt 2. That's total current. This value right here is I range 2.
Oh, so that's going to be 32 milliamps.
Yes. Does that make sense, Alan?
Yeah.
Because all we're doing is we split them apart earlier, but now when we look, if we have I meter and I shunt 2, those coming back together is going to be the total current going into this guy. So let me change this to that. Okay? So now we need to get R1 by itself. So we're going to divide both sides by I range 2. Those will cancel, and we're left with everything that we need to solve for R1. It's a what?
It's like the formula I was trying to draw yesterday for my Thevenin's.
Yep. These guys are a lot easier to draw to develop formulas than Thevenin is. So now, huh? So now we have our totals. R1 is equal to I shunt 2 times the resistance total minus voltage of the meter divided by the current for range 2. Do we have everything in here to solve for it? Yes. We have our I shunt 2, we have the total resistance, we have the voltmeter, and we have our range. So now we just plug these into our calculator and check out the answer. So we get 16.4 milliamps times our RST value, okay, minus 720 millivolts divided by 17 milliamps. Okay, here's one thing I want you guys to pause and look at. So while we're doing this, does this math make sense? What is current times resistance? Voltage. We're subtracting a voltage from it. So if the units are incompatible, remember, we can't just subtract ohms from volts. We can't subtract amps from volts and get the same answer. So we have volts, subtract volts, so that part's good. Then we have voltage divided by current gives us resistance, and we're looking for a resistance value. So this is where the units are very important to keep track of. Because if you screw something up in your formula, this will tell you you're wrong. Because your units aren't going to apply like they're supposed to. So R1 is equal to what? And as a double check, is that value smaller than our total resistance value? Yes. That's another way we can check to make sure we did this right. We should have values smaller than that total. Now, we went through a lot of calculations, a lot of substitutions with this guy. Was there anything else we could really solve for? We ran through pretty much every possible permutation through the circuit. Okay? So now we have R1 is equal to 115.508 ohms. And we have I shunt 2 is equal to I range 2 minus I meter. Everybody at least okay with how we got there? Like I said, I don't expect it to sink in like right off the bat, but logically, did I make anybody mad or violate any rules? Okay. So now, yes, this is as far as we can go in this range. So now, I'll switch to purple. We're going to come back up to our original circuit. We're going to flip the switch one more time, put us into range 3. So again, I'm starting to write down some of the information that we have. I'll keep this guy up. Let's go down and look at what is connected. So at range 3, what does our circuit redraw look like? A is connected to what? R3 and R2. Right here. What's R2 connected to? R1 in series or parallel? Series. What's R1 connected to? The meter. What's our meter connected to? R3 and B. Okay? Same things that we were looking for. What's our range current coming in? 125 milliamps. This current's going to split. We have branch 1. We have branch 2. So this resistance over here, we're going to call I shunt 3. And what current do we have flowing over here on the right side of our circuit? 600 microamps, which is I meter. Okay. So again, I shunt 3 is equal to what? Formula-wise. Other way. I range 3 minus the I meter. So I shunt 3 is equal to how much current? What'd you say it was? 124.4. Okay, again, now we're going to come back and look at our relationships. So the voltage of branch 1 has to equal the voltage of branch 2, correct? Okay. How do we get the voltage of branch 1? Yep, which we'll get there. So we know, so voltage of branch 1 is I shunt 3 R3, and the voltage of branch 2 is I meter R2 plus I meter R1 plus voltage of the meter. Okay? Again, we have two unknowns and we have one equation. So simultaneous equations aren't going to help us in this one. But what else will? Nope. The total voltage will be the same as the voltage across here. But individually, just remember, it's a series circuit, so it's going to take that total voltage and split it up amongst everybody. What can we do to get rid of one of these unknowns and replace it for something that has something that we know and something we don't? The same something we don't, I guess I should say.
Could we factor out?
No, there was two comments.
Never mind, can't do that. Okay.
Yep, can't factor those out. That's not going to buy us anything. What are you guys saying? Resistance total again. How can we change this formula to something we can use? Okay, we can move everything away from R3 because R3 is an unknown, and if we swap it out, we know this guy, we know this guy, we don't know these two. So if we can set two unknowns equal to each other, we can substitute that in and solve for it. So again, we have the resistance shunt total minus R1 minus R2 has to equal R3, right? That's what we were doing week 2 with series circuits in lab. Is we were given total resistances and we had to find them up, and they're broken up by the individual resistors. So we take these guys where they're equal and equivalent, we're going to substitute it in for this. So we get I shunt 3 multiplied by our R shunt total minus R1 minus R2 equals the current of the meter times R2 plus current of the meter times R1 plus voltage of the meter. Then we want to isolate the R2s because that's our unknown. We don't know what that is, but everything else we know. So we're going to distribute the I shunt 3 through everything. So we get I shunt 3 times the resistance shunt total subtracted from the IS3 times R1 and IS3 times R2. It is a lot of variables. But the thing is, we want to keep track of what do we know, what don't we know. This is easier than writing out the 600 micro and the 11 or the 115. Just kind of condenses it down a little bit. So now we want to solve, and we want to get all of the R2s together on one side, and we want to make them positive. So we're going to add IS3 R2 to this side. And then we're going to subtract from the right side the IM R1 plus voltage of the meter. And we're going to do an I meter R1 come on. So this guy's going to cancel out, that one's going to cancel out, and that one's going to cancel out from the other side of the equal sign. If you have to take this farther, if this is too confusing, put in other variables. You just have to keep a list of what you're swapping in and out. So all we did, we had our formula to make the voltages equal. We looked at trying to remove one of the two unknowns, and the way we can do that is by using our resistance formula. We manipulate this to where we get one unknown on either side of the equation, so we can just substitute it directly. In this case, we used R3, and that's equal to the total shunt resistance minus resistor 1 and 2. We substitute that in place of the R3 to get that out of our equation. And now we're trying to solve just for R2, which is this variable. So at this point, the electronics part of it is done. This is just algebra at this point. So we distribute the I shunt 3 through all three of those guys. And then we start moving things across the equal sign to get all of our R2 variables on one side of the equal sign and get everything else moved to the other side. Now we're going to rewrite it and simplify it. Everybody good up to this point? So we have I shunt 3 times the resistance shunt total minus I shunt 3 times the resistance of R1 minus I meter times R1 minus voltage of the meter. So that takes care of those 4 terms. All of that is equal to I meter R2 plus I shunt 3 R2. Now that we have all the variables we're looking for on one side, we can factor it out. So we have R2 times I meter plus I shunt 3. What is the I meter I shunt 3 value again? I range 3. Yeah, so the 125. So we're going to divide both sides. I meter I shunt 3 and our final equation we end up with R2 is equal to I shunt 3 R resistance total minus I shunt 3 times R1 minus I meter times R1 minus voltage of the meter, all divided by I range 3. So again, let's look and double check. Did everything we do work out correctly? Current times resistance is voltage. Current times resistance is, and again, is voltage. So we have a voltage value minus a voltage value minus a voltage value minus a voltage value. Are we good there? Divided by a current gives us resistance, which is what we're looking for. So now let's plug in values and solve for this guy. So R2 is equal to I shunt 3, which was 124.4 milli, multiplied by our shunt total, which was 163.636, minus 124.4 milli times R1, which we found last step, and the voltage of the meter, which was 720 millivolts. That whole quantity is divided by 125 milliamps. The cool thing is, going through this, we could go back through this entire exercise again. Oh yes, I meter R1.
So with every number right now that doesn't have a label, would those be ohms? Like the 63 and 115?
Yes, yeah, the 163 is an ohm, sorry. Yep. This is an amp, this is an ohm, amp, ohm, volts, amps, and ohms.
Why is it one? Oh, I agree. Okay.
When we plug this all into our calculator, R2 equals what? If you have to, break it up piece by piece. Solve for this for a voltage, solve for this for a voltage, solve for this for a voltage, and then subtract them down. Basically what this is taking into account, shouldn't quite be that high.
Yeah, that's what they were looking total.
I got 41.58.
I got 14.7.
Wow.
Graduate now.
I'm ready now.
So we have 20.356 volts. .369 volts.
And I got 41.583.
Yeah. So did I. In million.
I got straight numbers.
I have the closest answer without going them.
At this point, this just becomes an exercise in plugging stuff into your calculator. Like I said,
How did you get 47.343?
Yeah, I'm still 41 as well.
But I missed a step.
I'm pretty comfortable with 41.5.
that's 41.
So I'm guessing we're not gonna go back to range 1.
What?
I guess we're not gonna go back to range 1 and plug it all in.
No. Okay, so now, so it's 41. So now what we have R2 and we have R1. What are we left with? R3. We don't have another range, so that's all we can do is we go back to the very beginning and solve for this guy. And remember, we already have a formula that we just solved for to solve for R3.
Whoa! Hello. I mean, I like the shape, but I don't think that's what we need.
Yes, all that work for 6 ohms. But without that 6.5 ohms, we always have something in line with this, with our circuit, to give us the protection that we need to keep from maxing out and burning up our meter.
I don't feel like I really understand how this connects to something between those.
Because no matter how we switch it, if I can find it, because in here, when I disconnect the circuit, is there any current flow? If I'm in the process of switching the switch, it shuts it off so there's 0 current flow. Whereas, come on, shift over. Fine, I'll do it over here. Go ahead. Versus this method, when we switch in between these guys, we still have current flow going to the meter. So when we switch in between, all that current goes through the meter for a split second.
That's very scary.
So we're isolating it.
We're isolating our meter and changing ranges.
About that when you're growing it, is the A is gone.
Yep.
So high.
Yeah. That's the difference between these. Is this is how we can build a current meter so we don't blow it up when we change ranges. Explosions are fun, yes. Still does. But no matter what values I give you, we didn't use any values in here at all, did we? We didn't solve for the values until the very end. That is the formula for solving R1 in a 3-range universal shunt meter circuit. Every time. Every time. Because again, that's the reason I wanted to go through it like this. We didn't use a single value in that. It's not going to change what those values are. And then R3 is right here.
Yeah, I like our 3.
Yep. And then the last other formula you're going to need.
When we were still solving for range 1, this is really easy.
It is.
Then we got to range 2 and all of a sudden.
And you sort of drawing.
But like I said, what this is what electronics comes down to, is we're trying to analyze the circuits to understand how do they work so I can manipulate them to get what I want. That's really what it comes down to. And so with this, you guys now can go through, like I said, the long way to go through is you could, if you lost your notes, you could work yourself through this again to get to those answers. You could. It may take you some time, it may be difficult, but you could walk yourself back through these to get these formulas again. And that's kind of the idea with these, is we're not just giving you guys a formula to go, just to memorize this formula and then we're going to regurgitate it a bunch of times. These formulas come from places. They come from actual circuits. They come from things that we're doing. So yes, there is some memorization of formulas, but for the most part, you can derive just about anything you need to with the information that's given. Okay. We are at time for break. Give you guys a chance to decompress your brains, maybe put out a few fires. Hopefully nobody's brain exploded too terribly bad. When we come back, we will do some graphing, we'll do some simultaneous equations, and then I'll show you how you can do a bridge circuit using simultaneous equations.